Hello, everybody, and welcome to this episode of the Ampere Developer Impact. I'm joined today by Bhakti Hinduja, who's the Director of Customer Engineering at Ampere Computing. And we're going to talk in this series of interviews about performance analysis for customer workloads. What are the tools that are useful, the methodology that we use to identify when a problem can be worked around, or what a performance issue, to characterize a performance issue. And then some of the tooling that Ampere has created to help people do that performance analysis more easily. So today we're going to start with what is top-down performance methodology, and I'm looking forward to getting into it. So Bhakti, my first question is, I imagine that the conversation starts with a customer coming to see us and saying, this isn't working as fast as I expected it to. What's wrong? Right, at a very kind of general level, what are some of the first things you do when a customer approaches you to ask for help with a performance issue?
Yeah. So at the beginning, we ask them some questions about, hey, what environment is this problem occurring in? How often is it occurring? Is it reproducible? When you reproduce it, is there variance in your results? Like, does it happen only specific number of times in the day or at specific times in the day? Right, where there is peak traffic or something like that. Then we'll ask them for a reproducer so that we can look at the problem in an isolated environment, which is not a real production environment. That helps us sort of drill down further on the issue and really go to the root cause without getting distracted by other symptoms.
Okay. Do you also look for some information to be generated by the customer in the production environment, or what's some of the first tools that you run to see what's going on with the workload when you can reproduce it?
So Brennan Gregg, who's a colleague in the field, has a really good blog where he talks about some tools that we need to look for in the first 60 seconds. So, for example, tools that tell you what is your system uptime, message logs that will tell you about things like recent kernel errors or recent memory errors or any other hardware issues, right? These are basically you're just trying to catch any smoking guns at that point, right? So, any recent errors sort of point you to that.
So each of these tools is going to target a different part or a different subsystem of your operating system and try and figure out what's going on there, and that will allow you to identify a particular red flag. Is that the general goal here?
Yeah, that's sort of the idea here. So you're sort of eliminating issues or systems one by one and trying to get to the root cause of it. But the way to do it is basically structured so you don't miss on something that could have been a problem and rather drill down on something where the problem doesn't really exist. Which is why this sort of a structured list and like more like a checklist is really important to make sure that you're following it in that order.
Yeah, Brendan mentions in that blog post the use method, which is something I hadn't heard of before. Can you explain what the use method is and how it's useful?
Yeah, so the use method is basically stands for utilization, saturation, and errors, right? It is a systematic approach to eliminate every system that might be causing a problem for your application. So, for example, you can apply use method for CPUs, you can apply use method for the IO subsystem, you can apply use method for the memory subsystem, so on and so forth, right? So what you do is basically, for example, for the CPU subsystem, you first check on utilization. What is the utilization? Is that expected? Is that evenly distributed? Then you check at what's the saturation, right? Are you saturated on CPUs? And then you also look for errors. Are you seeing any errors? So following the use method through each subsystem kind of helps you approach it in a systematic manner.
And that's more about trimming parts of the decision tree that you don't have to pay attention to, right? It's about focusing in on what you want to look at.
Exactly. And the discipline and the completeness in this method is actually what helps you get to your problem soon.
Well, let's talk about that double click then. Once you've identified the subsystem that you've got a problem in, how do you go about figuring out what the nature of the problem is? Like, is there a particular set of tools or a method that you use to collect information more generally and then focus in on a specific kind of particular application or a particular function that's causing problems? Like, how does that work in general?
Yeah, good question. So let's consider you found a problem with your memory subsystem, right? So you did utilization, you checked your memory usage is pretty high. Then you looked at saturation and you figured that let's say you have a Java application that uses 32 gig of heap, and that's the only available memory on your system or your virtual machine. So essentially you're running out of memory, which basically means you have no room for things like OS caching or other OS related activities, right? So that's going to affect memory performance. And you might see out of memory errors in message logs or use other tools like we just discussed to spot those, right? So some ways to fix that would probably be then to drill down, use other tools that tell you more about your application, right? What your application is really doing at that point. So some of those tools are basically, one popular tool is just getting perf records for your application. So perf record is going to record what your application is doing, what kind of functions are being called as you're running your application, right?
Okay.
Um, and what you can do is you can do a top five analysis from the perf record stack. So it basically tells you what are your top five functions in your entire function call stack that are
Okay.
taking most amount of CPU cycles.
But so my understanding of perf is um, pretty basic. Right. My understanding is that it's going to analyze the whole system and it gathers events, right? I imagine that visualizing those events and figuring out where you need to focus on and figuring out, for example, what counters you need to zoom in on to see what's going on is kind of a key part of the system. Are there tools that help you figure out what's going on?
Yeah. So perf record is basically a statistical profiler, right? It will just sample CPUs at regular intervals and provide you a dump of that sample. And then you can set to what frequency you wanted to sample, you can set to the number of cores you wanted to sample on, or the whole system, how long do you want it to sample, so on and so forth. So all those are tuning flags that you can set in the command line as you record. Now,
Right.
after you record, you can use flame graphs, which are a very popular visualizing tool for visualizing this output. So what flame graph does is it stacks your function call, and the height essentially is your call stack depth. The deeper it is, the more function calls are present. And the width essentially represents the time spent. So wider means you're spending more CPU time on it, right? So this really
Totally.
helps visualize application profiles and where are you spending more time. And in a lot of cases where for performance engineering, we generally like to have like a good and a bad case, right? So let's say we found a problem, which is our bad case. We will try to convert it into an idealistic scenario, maybe give it more resources, right? So if it's a memory problem that we're trying to debug, we'll give it more memory, right? So that becomes our good case. That way we've eliminated that bottleneck. And now for something like flame graphs, we will see how flame graph behaves in the good scenario and the bad scenario. And that kind of gives us a visual way to then figure out what functions could be causing the problem because
Okay.
of our bottleneck.
Okay. So once you've used perf to characterize the problem, you figure out there's more time being spent in a function or a class of functions or some kind of system functionality than you're expecting in a
Mhm.
bad case versus a good case.
Mhm.
How do you then go about like approaching a mitigation, like figuring out what is actually going on and figuring out how to work around it? Because I guess, understanding why something is slow is all well and good, but you want to make it faster, right?
Yeah. So there are different ways you could figure out how to solve the problem. So for example, let's say you were using perf and flame graphs, and your perf top shows. Let's assume that you're solving a Java garbage collection problem, right? Your perf graph shows that there is some sort of a new object function that's taking most CPU cycles, and then that's when, let's say, 90% of your CPU cycles are spent. You also verify that through your flame graphs. Now, when you deep dive into that function and see what that function is doing, you probably see that it's creating massive number of objects, temporary objects for something like JSON parsing. And that's causing the garbage collector to be called every 2 to 3 seconds. And it's causing spikes in your response time because garbage collection is being triggered more so often because you're creating multiple temporary objects. So some of the solution for one of the solutions for something like this is to just reuse objects, right? Instead of creating multiple temporary objects, you just end up creating few objects and reusing it instead of creating new ones every single time for your
Right.
JSON parsing. Which basically drops the frequency of your garbage collection and then reduces your spikes, hence improves performance.
And so that's an example of an application-based mitigation where something is being done wrong in the application. You're doing too many SQL queries, or you're creating too many objects and destroying them too quickly. I imagine there are also certain classes of optimizations that are just purely system level tuning. Can you talk about some of the things that you can identify and maybe mitigate in terms of just changing the kernel you're running, or changing some BIOS settings, or systat settings?
Yeah, sure. So one of the problems that we recently had resolved was basically we had a system that was running Redis as an application, right? And we observed that the throughput coming out of multiple Redis processes running on that application was uneven. So we were not seeing the same kind of throughput out of each process running on that system. Now, Redis is a single threaded application. So the first thing we did for like root causing it was basically we pinned each application to each core. That basically binds the problem and helps us sort of root cause it further. Now, when we did this through a tool like mpstat, which tells us about uneven CPU load distribution, we were able to quickly identify that core 0 is specifically having higher time spent in the system time, higher IRQ utilization, as well as lower performance. So at that point, it was very clear that the rest of the cores have no role to play in this low or uneven Redis throughput problem. And that was that specific core that was causing this. Now, this was running inside a virtual machine on a host system. Upon looking at what the host system is doing, we found that the host system is actually using code 0 for all of its IRQ related activity, which means there is additional work that core 0 has to do in this case, which is beyond just processing Redis throughput, right? It's also doing work for host related IRQ activity. So that this is an example of how we can use system tools to even debug like these kind of issues. Ampere also has some of the tools that we've built for our developer community for to help with such microarchitectural analysis.
Okay. And we're going to look into some of those tools in our next interview, right? And in particular, there's the Ampere System Profiler and the Ampere PMU Profiler that give you a kind of an overview of all of the subsystems and where you can focus your efforts. Is that a fair summary of those two tools? I'm hoping it is.
Yeah,
Okay.
I'm excited to talk about it. And then these kind of PMU tools really help us with various characterizations. So, for example, it will help us identify what is the IPC of our application, which is a key metric when we are measuring efficiency of an application on a CPU. So, IPC is instructions per cycle, and that's basically computed by collecting PMU events, instructions, and cycles, namely. Then we can figure out what is our cache miss rate, what is the percentage of time that we are actually missing cache, right? We can also do a branch prediction analysis. What's our branch misprediction rate, for example?
And branch misprediction this is my high level understanding from Spectre and Meltdown, is basically the CPU is going to try and predict what is going to happen after a branch instruction and then pre-calculate some of those instructions in the CPU pipeline. Is that right?
Exactly. And branch misprediction is when CPU incorrectly guesses the next set of conditional jumps or any if-else loop that it will take, and it keeps the instruction pipeline full, but it's essentially not doing that.
Right.
It's mispredicting that basically.
That's wasted
So
work, basically.
yeah. So when that happens, when the misprediction happens, and why that is so important, the CPU has to discard all the work in its current path and then restart fetching instructions again, and that causes some performance penalty due to these wasted CPU cycles.
So thank you, Bhakti, for joining me today. This has been a fascinating tour of the operating system level tools and the methodology that you use to characterize and fix performance issues. Would you like to give a kind of an overview of what the methodology is in general and why it's important to follow it so closely, just for our audience, before we look at some of the Ampere tooling in our next episode?
Yeah. So as I mentioned, it's really important to kind of follow this structured process, and that's where the beauty of systems performance engineering lies. So that way we don't get distracted into any kind of false error scenarios and are truly focused on the real root cause. So it's important we always start with methodology first and not tools. So oftentimes I see folks throwing all the tools at the problem and then trying to get something out of those tools. So that's where the use method is really helpful. You're kind of forcing yourself through the methodology, utilization, saturation, and errors, and you're going through every subsystem following that, right? And once you finish your system level characterization, that means you have eliminated any bottlenecks in your CPU, IO, memory, storage kind of subsystems. Then you drill down into figuring out where are application level bottlenecks with perf, records, flame graphs. And then after, let's say you don't find something glaringly wrong at these 2 points, and then you start doing microarchitectural analysis to figure out what's going on in the CPU microarchitecture with respect to your problem, right? So this following this structured process is very important to kind of get to the root cause. Some of the other key points is like always measure twice and optimize once. So one change at a time, and make sure you're measuring at least 2 to 3 times to kind of figure out if that change has actually impacted your experimentation, right? And then go deep when necessary, know when to go wide and know when to go deep, right? So when you spot a problem, you have to go deep to figure it out. Otherwise, you just keep going wide and those kind of things. So like I said, it's really the beauty of this systematic approach. And that's why this methodology and the tools around it are so important to figure out the problems, right? And with AI, as our work and our systems get more distributed in nature, I'm excited to see, the future of observability and performance engineering evolving. So this is a very exciting space to be in.
Me too. And thank you for providing that systemic overview of how you approach the problem. I really like it. It reminds me a lot of kind of outage drills that really experienced operations teams do. It's like you don't change anything until you've taken a situational awareness of what's going on, and then you change one thing at a time. Did it fix it? Did it not? I really like the approach. Thank you very much for introducing it. And I look forward to seeing you on our next episode when we look at some of the Ampere tooling that's there to help developers do that more effectively and more efficiently. So Thank you again for joining me today, Bhakti, and I look forward to seeing you on the next interview that we have on the Ampere Developer Impact.
Thanks. It was fun being here. Thanks, Dave.